Have you ever wondered how hacker pros are able to keep their fingers on their keyboard? Have you tried setting up a similar workflow and even thrown away your mouse, only to have to pick it up again because the IDE forces you to press a button? I understand, and that's why I'm going to show you how to program an embedded system without an IDE in this video. And while the hoodie is an obvious advantage, I promise there are more benefits to adopting this workflow. Hi, it's me. I'm back with another video in this video series about programming an embedded system from scratch, this robot. In the last video, I set up the integrated development environment, the IDE provided by the vendor for the microcontroller on this robot, the MSP430, and I managed to compile and load a simple example project that made the LED blink on this evaluation board that has the same microcontroller. And using an IDE is all fine and dandy, but I also mentioned there was another way to do this without an IDE, and that's what I'm going to show you in this video. Okay, so with an IDE, as we saw, compiling and loading code is just a matter of pressing a button and everything just gets magically taken care of. But of course there is no magic going on, and what's actually happening is that there is a set of tools underneath that does the heavy lifting. A toolchain that most importantly include a compiler that takes the code we write and translates it into an executable that can run on our target, in this case a microcontroller. And to some extent we can see the IDE as just a GUI wrapper around this toolchain. And in this video I'm going to discard the GUI part, that is the IDE, and jack into the toolchain directly from the command line. And while I can use the toolchain included by CCStudio by default, I'm going to install another toolchain because there is actually more than one toolchain that supports the MSP430, and this is commonly the case for most microcontrollers. And then I'm going to run the compiler in this toolchain as a single command from the command line to build the same example project as in the last video. But running the compiler this way is inefficient and cumbersome, and that's where Make and Makefiles come in. And to show how Make and Makefiles work, I'm going to create a new Makefile from scratch that will be suitable to use as a starting point for the project in this series, but for any microcontroller project really. And to clarify, jumping out of the IDE is not merely an exercise to make things more complicated. There is actually some real advantages to it. We're not bound to an IDE anymore. You can actually start setting up a development environment more to your own liking. You can use your own editor of choice, your own terminal and your own tools basically, and customize them in a way that makes for a more pleasant workflow. And another good thing with such a setup is that you can reuse it across projects and actually improve it over time, instead of having to relearn a new IDE every time you change target. And these IDEs also vary in how good they are. Some IDEs are acceptable, like CCStudio, but some IDEs are also quite horrendous. Another important aspect is build automation, which is a given in larger and more serious projects, especially in the professional world. We want our code to be checked and tested. I mean, a person makes a commit, and this commit runs through an automated system to check it for errors, and perhaps we run some unit tests, and we want this entire chain to be automated. And trying to automate this using the IDE is going to be near impossible, because CI system wants to run commands and not press GUI buttons. Automation overall is just so much easier if you have a command line based workflow in place instead of an IDE. Another advantage I think is understanding. One of the reasons I went into embedded systems to begin with is because it's a field or subject that allows me to actually dive deep into how things actually work, and an IDE is really a barrier against that. And when you interact with the toolchain directly, it forces you to understand more about how the build process works. And not only is that more satisfying, it's also tremendously helpful when you run into build issues, which you eventually do regardless if you're using an IDE or not. Okay, toolchains. I already have a toolchain installed as part of the installation in the last video of CCStudio, and this is a proprietary toolchain that TI supplies. And while I could technically use this toolchain from the command line to build my code and also use it from a Makefile, I'm not going to use this toolchain and instead install another toolchain called GCC or GNU Compiler Collection. Probably a toolchain you're already familiar with if you have ever compiled a C program on Linux, because it's the standard toolchain that comes with most distributions of Linux. And it's a toolchain that's widely used and supports many different architectures. And it's used in large projects, most prominently perhaps the Linux kernel, So overall, a very popular toolchain, and it's good to be familiar with it for this reason, because if you learn this toolchain, you will probably have use for it in many different projects. And that's one of the reasons why I want to use it instead of the toolchain that the TI supplies, because their toolchain is only applicable to MSP430 microcontrollers. Another reason is that since GCC is so widely used and it's also open source, it's also better documented, which is an important aspect when you consider using the toolchain directly, because then you want to understand how to use the toolchain. For example, you want to know what flags or options you can use for your compiler and what they actually do. It's also a free toolchain, so you don't have to pay for it. And yes, I know TI compiler is also free, but you may run into other microcontrollers where that's not the case, and where you instead have to pay for the full version of the toolchain that the vendor provides, but at the same time has support for GCC, and in those cases you have another reason for why you would want to use GCC. Relating to this, there is also other toolchains developed by third-party companies, such as IR Systems, Keel or Crossworks, and these companies develop full toolchains and they have their own IDEs that can be used to develop code for several different architectures, including MSP430. Their selling points is typically that they produce smaller and faster binaries, as well as provide better technical support. But of course, to get them, you have to pay. So you're probably not going to be using them in a hobbyist level project. And I have no previous experience with them, and I'm not going to use them here. But I think it's good to be aware that they exist, because you may run into them in a professional setting. Okay, so now I'm going to head over to TI's website again to download the GCC toolchain. The version of the GCC toolchain or compiler that the TI offers here is one that they own and actively develops. This is different from the mainline GCC, and I think some of the support for MSP430 has actually been ported into the mainline, but I'm not sure to what degree, and it's just gonna be a better bet using the one that TI provides here on their website. And as I mentioned in the previous video, I am on Linux, and it's going to be preferable to be on Linux when you start working from the command line, because Linux simply has a better command line experience. And of course there is another 100 reasons why you should be on Linux, but let's not go into that right now. Yeah, I've obviously downloaded this before, and I can just show you that I can unpack it. And then all the tools are available inside this unpacked folder. Yeah, so here you have some of the different tools, most importantly the compiler. Now obviously that's not going to do anything unless I provide an input to it. But since I have already unpacked this in another place, more specifically in my home folder under dev and tools, similar to where I installed CCStudio, I will be using this path from now on. And one thing I can also show is that you can work with this toolchain also from CCStudio by making sure you add it to one of your available compilers inside CCStudio. So then you would go into properties and choose your compiler version here. But before doing that, to make it available here, you would have to add it and find a path to it, and yeah, simply add it. And then you can build your project with the GCC toolchain from CCStudio. But I'm not using CCStudio in this video, so let's move on. So what I'm going to do now is I'm going to build that same Blinky project that I built in the previous videos using CCStudio, but I'm going to run the compiler from the new toolchain from the command line to build this project. And to make this a bit more convenient, I'm going to add my compiler to my path, so I don't have to type the entire path each time I invoke the compiler. And the simple way to do that is just to update the path variable. And just to confirm, I can echo it. Oops. Like this. and as you can see, I've added the current directory where all the tools are available to my path. So what I can do now is simply write it like this. Yeah, and let's now head over to the folder where the Blinky project is. And that's going to be located in the workspace I created in the last video. And let's try to invoke the compiler to build the Blinky project, just doing it like this first. And now you will see that I will get a couple of errors, because in order for this to work, I also have to add a couple of options to the compiler. Okay, the first error we get here is that the compiler tells us that it can't find this header file. And I talked about this header file in the last video. It's a header file that contains some useful definitions when we are working with the registers of the microcontroller. And this header file is provided by the vendor, that is Texas Instruments. And the reason the compiler can't find this file is because we haven't told it where to look for it. And this file is located inside, well, for one, it's included in the directory of CCStudio. But it's also part of the toolchain that I just downloaded. So what I'm going to do now, I'm going to add another directory to the search path so that the compiler can find this file. Okay, so first of all, let's have a look at where it's located. So yeah, so it's located in this include directory. Okay, so the path I want to add to the search path is this path. And the way I do that is by using a flag, large I. And now I can run this again, and I should get another error. Yeah, and now it starts complaining about these definitions that we expected to be declared inside this file, that they are not declared. And the reason it doesn't think these are declared is because this header file that we just told it where to find, it's not only used for the particular microcontroller I'm using here, but it's also used for other microcontrollers. So in order for it to match up with this microcontroller, I have to tell it which microcontroller we are compiling for. And as you can see in this file here, we have this large if-else define here. So what I have to make sure is that the appropriate define is defined. And one way I could do that is to simply write define underscore underscore inside the source file. But there is a better way to do it, and the way we do that is add another flag. And that flag is -mmcu. And then we can tell it which microcontroller we are targeting. And besides adding this define, this flag also does a couple of other things. For one, it tells the compiler which ISA we should use, that is, which instruction set architecture. And it also tells the linker which linker script that should be used. And the linker script is basically a script that describes the memory layout of the microcontroller, so how big it is and where things are located, such as peripherals and so on. And if you aren't familiar with the compiler or linker, in short, what the compiler does is it simply just translates each source file to an object file, and then it's the job of the linker to bring all of these object files together into one big executable. Of course, it's a lot more complex than that, but I don't want to go into the details in this video. And if you want to know more about how it works, there is a lot of resources on the internet. So if I run this now, I once again get another error. This is because while the flag we just added tells the linker which linker script we use, it doesn't tell the linker where to find this linker script. And the linker script is actually located in the same directory as the header file that we just helped the compiler locate. So it's in this include directory, and I can actually open it up. It's going to be named like this. And as I told you, it contains information about the memory layout and yeah, lots of other things here, which I'm not going to go into right now. Okay, and in order to tell the linker where to find things, we have to use the L flag instead. And we can use the L flag with the same path as we just added to the I flag. So like that. And now if we run this again, it succeeded. So now I've actually compiled the Blinky project from the command line without involving CCStudio. And as you can see, I have the binary right here, the A out, which is a default name if you don't tell it what to call. But I can also run the command with O flag to define the name of the output. So for example, I could name it blink. And then the output is named blink. One thing you may wonder is how I knew which option I needed to use in order to make this compile. And the way I knew that is I read the documentation that TI provides on their website, and it's located on the same page as where I downloaded this. So under technical documentation, and then there are a couple of guides here. And this is pretty well written, so if you go through this, you will find out which flags you can use and how they work. Another trick you can use to find out which flags to use is to actually look at what CCStudio uses to build the example project. So I'm gonna just create a new project now because I wanted to use the GCC toolchain instead of the TI compiler. Now for some reason our target is not available in this list as it has been in previous CCStudio version. So just for the sake of this example, I'm going to just pick a similar target so we get similar flags. So I'm gonna use this target here, and then I'm gonna use the blink example, blink GCC. Let's go. And now if I build this, I can have a look in the console here to look at what flags it's using to compile this program. So it's invoking the compiler and linker separately, and here you can see a couple of the flags it's using. Yeah, and we can break these flags down. Let's copy them to my editor instead. We have this -c flag here, and that just tells the GCC to only run the compiler, since they run the compiler and linker separately. And that's what we're going to do later when I write the Makefile as well. And then they have this flag that we've already defined. And then they have another flag here, which tells the compiler explicitly that there is no hardware multiplier on the microcontroller. And what this means is that there is no dedicated hardware to handle multiplications. And this means that when the microcontroller does multiplication, it has to do the computation in software, which requires more instruction and is slower. And this flag just tells the compiler that it has to use this code and can't rely on a hardware multiplier. And I think we don't need to define this flag anymore. I think this was a problem before because none was not the default, and the default was that the compiler assumed that there was a hardware multiplier. But I haven't used this flag in my project, and I haven't had any issues with the multiplication, so I don't think we need this anymore. So I'm not going to add it to my command. Yeah, and then we have a couple of I flags here to add search path to different directories, which we have already done. And this -oj flag sets the optimization level. So there is different levels you can set here, 1, 2, 3, and so on. And the J flag is basically a compromise between optimization and the ability to actually debug the code with a debugger. So this is a good flag to use when you're developing code. And then the -j flag is a flag that tells the compiler to add relevant debug information for JDB. And JDB is the debugger that's part of the GCC toolchain. And then there are two flags here referring to dwarf. And I'm not very familiar with the dwarf, but that's another format for debugging information basically. But I'm not going to concern myself with those. And then this -wall tells the compiler to turn on all warnings. So when we define this, the compiler is basically going to complain about everything. And then there are some additional flags I'm not going to use or concern myself with. Okay, so now I'm just going to add these flags to the command we just ran, because we're going to want to have them when we compile our program. So we're going to want to have O-J as well as -j and -wall. And we can run this again to make sure it compiles. One thing we can do is to see that it actually makes a difference is to check the size of the binary. So if we if you check the binary with the flags on, it should be larger, I think. Yes, so since these flags change the optimization level as well as add debug information, they obviously make the executable larger, and that's what we're seeing here. Okay, so now I haven't actually tried to flash the executable to the microcontroller, but I will do that later in the Makefile, and you will see that it actually still works. Okay, so what I would like to do now is make this project a bit more complicated, or not complicated, but I want to break out some things into a separate file, so we have multiple files we're dealing with, just so you can see how we compile when we have multiple files, and you can see how that becomes more cumbersome. So what I'm going to do is break out the LED specific stuff to a separate header and source file. So let's create those files now. Okay, so let's open the main file as well as the LED files. I'm going to create two functions for the LED related functionality. One function to initialize the LED, that is to configure the GPIO port that's toggling the LED. I'm just gonna name that LED init, and then I'm gonna I have to give it a return value as well. Put that void, and then a function to actually toggle the LED, and I'm gonna name that LED toggle. And I'm setting the argument to void here because that's good practice in C. And this is because in C, if we leave this empty, it actually says that the function can take a variable number of arguments of unknown type. And if that's not what we mean, we should write void here. Okay, so switching to the source file. Let's first include the header file. And then define these two functions. Okay, so this init function is just going to be one line. It's going to be the same as this line here. So let's copy that. And then the toggle function will also be a one-liner. It's going to be this line here, so let's copy that as well. And then we should include the LED header file in this file and replace these with the functions instead. So LED init and LED toggle. Okay, so now if I run the same command again, this should fail to build because it couldn't find the LED function, because I haven't told it to also compile the LED source file. So let's add that to the line. And now it says that it can, yeah, and that's because I haven't actually, I need to add this line as well. So now if I run it, it should build, and yes, it does. Okay, so I get all of these warnings inside my editor here. So because I haven't set this up properly for this project, so I'm just going to disable these for now. And the editor I'm using here is Vim, and it's quite a quirky editor because you have to learn all sorts of key bindings and commands and configure it to be able to work efficiently and effectively in it. And it's quite a steep learning curve, but once you get used to it, it's actually pretty nice. I'm not sure I would choose it if I were to start over today, because I mean there are better things you can spend your time on than learning a new editor. And there are also many other good editors available these days, such as VS Code. But this is just one of the aspects that's really nice when you work from the command line like this, because then you're really free to choose whatever editor you like, especially if you work in a project with several others, because then everyone else can choose whatever editor they like as well. And you know, everyone has different preferences. but at the same time you can share a single common way to build a project. Okay, so now I have this way where I can build the project from the command line with a single command, this command here. And while this is kind of acceptable right now, what you may realize is that once this project grows to be more complex, when we add more files, then it's going to become quite cumbersome to have to run this command every time, and it's just going to become one long line that's hard to read and keep track of. And it's also going to be inefficient if we run this command every time, because what this command does, it compiles everything from scratch each time. And while it isn't noticeable right now, for a very large project, this is very inefficient to do, because if we just change one text file, we don't actually have to recompile the entire project. We only have to recompile that file. So it would be nice if there was another way that could make this easier. And this is where make and Makefiles come in. And a Makefile is a file that describes how to get a certain output from a set of inputs, which is often executable from a set of source file, but it can be other things besides that, which I'm going to show later in this video. And Make is the program that processes the Makefile. And Make keeps track of if the inputs has changed and if it has to recompile a certain part of the output, which means it solves the problem of having to recompile everything every time. In other words, in this case, the Makefile can act as a way to organize and keep track of our build process, instead of us having to remember this long command. And if you're on Linux, you probably already have Make available to you. Okay, so now I'm going to create a new Makefile from scratch to build this project. So let's first create an empty Makefile and open it. As I said, a Makefile describes how to get a certain output from a set of inputs, and our output in this case is the compiled output, this binary here, blink. So let's define a new rule for this. So this is going to be our output here, and then the syntax is that we put a colon here and then define our inputs. In this case, that's going to be the two source files, main.c and led.c. And then on the next line we describe the recipe on how to get the output from these two inputs. And we must make sure that this is tabbed and not spaces, because that's how Make parses it. And here I'm just going to copy the command that we just had. Now we can just write Make here, and Make will just assume that there is a Makefile in the current directory. And now, since the output already exists, Make is just going to say that the output is up to date. So let's remove the output and run the command again. Yeah, and since this line is a bit lengthy, we can break it down using backslash. And this is like the simplest Makefile we can create for this project. I mean, while we have already gotten some benefits from Make, there's still a lot of things we can do to make this Makefile a bit more general. I mean, easier to extend if we start adding more files, add more options to the compiler and so on, as well as making a Makefile that is easier to reuse across different projects. And I should also say that there is no perfect way to write a Makefile, and it often just comes down to personal taste. And what I'm going to show in the rest of this video is how I prefer to do it. But of course there are some good practice tests you will find in most Makefiles. Okay, so the first thing I like to do is create a set of variables to make this command a bit more readable. So starting with the directories. And first I can just define some variables for where to find the toolchain files. And like the way you refer to a variable is using the $sign and parentheses like this. And now I can replace some of the things in the command as well. And then I also like to create variables for the different commands I use in the Makefile. So starting with the compiler, I typically name that CC, and that's one of the practices you see in most Makefiles. And then I can replace this inside the recipe as well. And then another thing I would like to give a name is the output. So the target. Then I can replace that here. And now we can run Make again to make sure that this still builds. First let's remove blink. Yeah, and it works. And I've also added a couple of comments here, as you see. And the way you add a comment is by adding a hash symbol like this. And I just add these comments to make the Makefile a bit more readable. The next thing I like to do is separate the flags into variables as well. So let's start with a variable for the microcontroller name. And then let's create a flag for the warning flags we want for the compiler. And the ones I'm going to put here is, first of all, wall, which I already mentioned enables all warnings. And then I'm gonna add w error, and this makes all the warnings appear as errors, which means we can't compile our program if there are any warnings. And this is just a good way to ensure that we never let any warnings through and actually fixes the warnings as soon as they appear. It's just generally good practice. And there's also another flag I would like to add before this one. It doesn't really matter which order they come in, it just makes more sense to me to put this before the w error. And this is w extra, which enables some additional warning flags that are good to have. And as I said before, if you want to know more about what these options do and what kinds of warnings and so they enable, you can just take a look at the general documentation of GCC. And finally, one additional warning I would like to enable is shadow, and that's just to get a warning or error if I accidentally name a variable in a nested scope the same as a variable in the outer scope. There's actually a good blog post about good compiler flags on a blog called Interrupt Memfault, and I will link that in the description. And next I want to have separate flags for the compiler and the linker. So I'm going to include the warning flags for the compiler. And then add the specific linker flags, which is going to be the MMCU flag using the MCU variable we just defined. And next I could just write -l and simply write libbeers like this, but I don't want to do that because in case I start adding more directories I would have to break this up into multiple variables and make sure I use -l before each directory. And to avoid that I'm going to use a make function called add prefix. And this function adds a prefix to every string in a list of strings, and the list of strings in this case are the directories. And I'm also going to do the same for the include directories to the compiler. And to the compiler flags I should also add the optimization and debug flags. And now let's replace them in the recipe as well. And we can shorten this even further now and keep it on one line. So let's remove blink again and run it. Now we got an error. We can actually see the entire command that was run, and it's this one here. And we can notice that I accidentally made a typo here and used the same prefix for both the linker include as well as the compiler include. This should obviously be -i, so we have to fix that. And now it works. Okay, so the next thing I'm going to do is separate the compilation stage and the linking stage. And the way I do that is by using the -c flag, which tells the GCC program to only run the compiler. Let's do that for the two files. And the output of the compilation stage is an object file and not the complete executable, and that's why it has an ending like this, the .o. And then add a C flag to tell the program to only run the compiler, and the output and the input. And then we have to do the same for the LED file. And separating it like this is what's going to let Make work more efficiently by only compiling the things that actually need to be compiled. And then we should replace the input here with object files, as well as here. And I previously forgot to replace this with target as well. And we can add a comment here as well and say that this is the linking. And we should remove the compiler flags. because we are only linking here, and we don't need to add a specific flag to link here. It's going to recognize that it's object files and just do the linking. So let's remove the output file again and rebuild this. Oh yeah, and now we also have to add the -mmc flag to the compiler. And as you can see now, it has first built two object files for the main file and the LED file, and then it does the linking in the third step here. So if we look into the folder, we can also see these separate object files. Of course, we don't want to repeat the compilation stage like this for every file. I mean, it's acceptable when we only have 2 files, but imagine having a lot more files. Then it's going to be really tedious having to do this for every file. So what we're going to do now is instead use some Makefile tricks to avoid this. First off, I'm using the % sign here to match any output with the ending .o. So when make reaches this line here, it's going to see that it requires these prerequisites or these inputs, and then it's going to look for how to generate those inputs, and it's going to find a match here because it's going to match this output right here. And once it matches that, it's going to replace this ampersand here with the match it made here. So for example, for main, it's just going to replace this with main. And since main.c is a file that exists in our directory, it's going to be able to run this recipe. And to avoid hardcoding the name here, we can instead refer to the output and input using special symbols. So for the input, it's going to be this $sign and this upper sign. And for the output, it's going to be the $sign and the @ sign. And then I can remove the line below. And I can also replace these two with the $sign and up sign as well. Well, I don't need to use target here either. I can also use the $sign and @ sign here too. Let's remove the object file and the output file and run this once again. And yeah, as you can see, it works as before. And now we avoid repeating ourselves for every source file we add. Of course, it takes some time to get used to these cryptic symbols, and that's why if you aren't familiar with Makefiles before and you open up a new Makefile that someone else has written, it can be a bit cryptic at first to understand what's going on. But I think if you write a Makefile from scratch like this, it's going to be much easier to understand what's going on. One thing I would also like to improve is that right now we litter the main folder with all of these object files and output files, and I would like that to get generated to a separate directory instead. So what I'm going to do here is define a new build directory and a separate directory for the objects files, and a separate directory for the final executable. And I'm also going to put the files I'm compiling into a separate variable as well as the object files. And then let's replace that in the rules below. And just to make sure that the folders exist or that they get created in case they doesn't exist, I'm going to add just a normal command line command here, which is the program used to create directories in Linux. And I'm going to add a -p flag here just so it doesn't give me an error if the directory already exists. And then I'm going to use the dir function here to get the directory of the target. So I could either just write target here, or I could, as I did below, use the special symbol to get the target as well. And I'm going to prefix this with an @ sign just to avoid having this printed like these lines here, because I'm not really interested in seeing that the directory was created or that this command was run. And then I'm going to do the same for the compilation stage. Okay, so now if I remove the object files again as well as the output, yeah, we can remove this one too, and run this again. And now we should expect the generated files to be put in a separate directory. Oh well, I also have to prefix the output of this rule with the object dir as well.
Oh, and yeah, this should be named LED and not blink. And there we go. Now we have a separate directory, but it didn't actually build the main file. Oh well, the target we should also add a prefix this. Now we should have all the, yeah. And then the object files inside here. Yep. Okay, so now we're still kind of repeating ourselves here with the source files and the object files. I mean, if I add a new source file, I have to add it both to this variable as well as to this variable. So what I'm going to do now is make sure that I only have to add it to the sources variable here. So I'm basically going to create the object variable from the sources variable. And the way I do that is first replacing the suffix of each source file of the sources variable. And I can do that like this. And this is just a built-in way to replace the suffix of a list of strings, basically. And then I can use a function called patsubstitution to prefix each source file name with the object there. And all the special make functions I'm using here are documented in the make documentation. And then take object names. Come to think of it, I might be able to use the add prefix instead of the path substitution here. I don't quite remember why I used path substitution here, but I guess there might have been a reason for that. So let's not try replacing it with add prefix for now. Then I can remove the objects here. Okay, so this way I can, okay, so let's see, you see so that it works as well. So remove the build directory. It does not work. Oh yeah, I see what's wrong. There shouldn't be an H here. Yeah, and it built again. Okay, so this way, every time I add a new source file, I can just add it to this variable. And while I could simplify this further by having the Makefile add all the C files automatically, I don't want to do that. I much rather prefer explicitly adding each Makefile separately, because it just gives me more control and just reduces the chance of me spending a lot of time figuring out the compiler, or only to realize that I accidentally tried to build a file that I shouldn't build. Okay, so as I also mentioned before, a Makefile is not necessarily only for building things. You can also do other things with these recipes here, and where each rule or recipe doesn't actually have to produce an actual file. The way we can add such a recipe is by defining something called Phony targets. That is fake targets. And two Phony rules you will often see in Makefiles are all and clean. All is just typically used to build everything, and clean is to remove all the output, basically clean the building directory so that you can rebuild everything from scratch again. And in this case, that's going to be removing the build directory. And I'm also going to separate this command into a variable. Okay, so now if I run make clean, it should remove the build directory. And then if I run make all, it should build everything again. And the reason we have to set them as Phony here is because if we don't set the target as Phony and there is a file with the same name, it's not going to run this recipe because the output will already be satisfied. So let's say I just, for example, add a file named clean and I remove clean from here, and then I try to run make clean. It's just going to say that clean is up to date. So that's why we need that. Now, one last thing I want to show from the Makefile is that we can actually add a rule to flash the compiled output to our microcontroller. So once again, let's add a couple of more variables. And I'm going to use the debugger that's available as part of the CCStudio installation I made. So let's add a variable for the directory where the debugger is located. And then some additional variables. And then add the actual command. And then finally create a rule for flashing. And then add it as a phony target because it doesn't generate an output. And then we need to add tlib here for this microcontroller because this debugger supports different microcontrollers and can load different drivers, and the driver we need is this one. I'm not going to go into details about this debugger here. I made a blog post a while ago where I described this whole process a bit more in details, and I'm going to link that in the description as well. And this program command will erase the flash and then program the flash with the target. So now if I plug this launchpad into my computer, as in the last video, I should be able to just write make flash to build and flash the program to the microcontroller on this evaluation board. As long as I don't make any stupid typos. And now it's flashing, and now it's done. And as you can see, the LED is still blinking. Okay, so and just to confirm that it's actually working, let's uncomment the line that toggles the LED. And I also saw that I missed another thing. I should add target here to make sure that we actually build the target before we flash it. Now if we run make flash again, we should expect the LED to stop blinking. And as you can see, it stopped blinking as expected. This was everything I wanted to show with Makefiles in this video. There's of course much more you can do with Make, but I think this is a pretty good starting point, and I will use this Makefile throughout this video series to build the project for this robot. I might add a couple of more lines to the Makefile, but overall this Makefile is pretty much going to look like this through the entire series. And I also think it's not just a good starting point for this project series, it's also a good general starting point for a Makefile for smaller microcontroller projects. So you should be able to easily use it in one of your own microcontroller projects. Another thing I should mention is that modern projects often use CMake these days. And CMake is similar to Make in that it enables you to build your project from the command line. But instead of actually producing executables, CMake sits one level above and produces build files. So it's able to generate make files, but also build files for other build systems such as Visual Studio or Ninja and so on. And CMake is really powerful when you want to build a project for multiple platforms or generate files for multiple build systems. And I could have used CMake for this project as well, but it's really overkill and I wouldn't gain much from it, and just using a bare Makefile is very reasonable for a project of this size, and you don't have to always use CMake these days. But there is one advantage to using CMake even for a project like this, and that's if you are using an IDE or a editor that can parse CMake files, because then you can actually build your project directly from your editor and probably get some better linting and so on. So that can be something to consider if you're using an editor that supports that. Just to recap a little, I've showed you two workflows for developing code for microcontrollers, or really for any C/C++ project. In the last video, I showed you how to use the integrated development environment provided by the vendor. And in this video, I've showed you a command line based workflow where I use my own editor of choice together with a Makefile. And the command line based workflow is the one that I prefer because there are several advantages to it, as I've already already mentioned. And it's the workflow I'm going to be using most of the time throughout this video series. But I will also open the IDE from time to time. And I'm probably going to open it more than I usually do, because there are going to be things that I want to show. With that said, if you're new to embedded, I don't think you should overcomplicate things by stepping into a command line based workflow immediately and create your Makefile and all that, because you have enough on your plate as it already is, and it's just going to be easier to be sticking to the IDE to begin with. But it's of course good to be aware of what options you have when you start becoming more comfortable. And to be honest, the benefits of a command line based workflow or a Makefile is not obvious for a smaller project like this robot. And it may seem a bit tedious and time consuming having to create a Makefile, but once you have a Makefile in place, you can pretty much reuse that for most of your project, and especially if you use the same toolchain. The last thing I want to leave you with is that if you go down the route of the command line based workflow, try avoiding getting stuck in the endless loop of tweaking your development environment to perfection. I have been there, and I still have a lot of things I would like to improve with my development environments, including my editor and the tools I use. But I think it's just better to get something up that is good enough and then let it organically evolve over time. And the same goes for Makefiles. Start simple. So that was all for today. If you have any questions or feedback, please leave a comment below, and see you in the next video.